is also a very important bit for assuming.
So good morning. So I'll be presenting SimCLR, a simple framework for contrastive learning on visual representation. So first I'll start with supervised learning. So in the domain of supervised learning, we know that we have the images, we have the labels. So giving these labels to these images, you have to manually annotate these one using human by a human. So this is really time consuming, and also it's a cumbersome task for large data sets. So even if we stick to this label data, that is a very low percentage of the whole data we have in this world. So if we stick to supervised learning, we are leaving a lot of unlabeled data on the table. So the obvious question is, so is there any way of exploiting those unlabeled data? So how can we learn any good representations from this unlabeled data? So the problem is unsupervised representation learning. So in terms of that, the domain of self-supervised learning tackles this problem. So mainly self-supervised learning was implemented in NLP tasks. So with this paper, we'll find out how it was implemented in the computer vision task. So simply a self-supervised learning is, it tries to automate the generation of input and label pairs. So without any human interaction, it generates the labels from the images. So once we automate the task, we get the self-supervised model and use fine-tuning to do any downstream tasks like image classification. So, but how are we actually doing this automation? So mainly we have pretest tasks. What does pretest task do? So for example, like we can give an image and we can puzzle it like this. So what the neural network should learn is how to order these separate samples of the image. So the intuition here is the neural network learns the general features of the network to do this task even without the label of the images. So likewise, we can use a huge unlabeled data set and use a feature extraction layer to do the task, and then use these feature extraction layers in downstream tasks and fine tune it to do a more task with human labeled images like image classification. So then in the domain of contrastive learning, so it's under supervised learning. So it learns general features of an input by learning what data points are similar and what are different. So likewise, the cat image. So the neural networks tries to find what are the similar images to this one. Similar images and the others are different. So if I revisit unsupervised learning again, it can be categorized into mainly two parts. Generative modeling. In generative modeling, we generate or model pixels in the input space. So this pixel level generation is computationally expensive. And the other one is the one I talked earlier, discriminative modeling. So we are using pretest task to learn representation from an unlabeled dataset. So these pretest tasks are heuristic. So normally this trial and error, you have to do trial and error and get the best one. So most of them are like ad hoc and maybe limiting. So when it comes to SimCLR, so it's using self-supervised learning on ImageNet dataset. So as you can see, the SimCLR model already outperforms the previous self-supervised learning algorithms, also going to the level of supervised learning accuracy with the increase of the width of the network. So if I were to talk about the SimCLR framework, what they are doing is they are getting an unlabeled image and applying two different combinations of augmentations. So likewise, they get an image and give two different augmentations and feed that into a base encoder model and get the representations here. And then again, they feed into a MLP layer and get these embeddings. So the intuition here is if these images are similar images, so they should have high level of high score of similarity, like attracting. The other images should have a low level of similarity. So this layer, so they use random crop and color distortion for augmentation. So these are some examples of augmentations they have used. This is the original image, and these are some augmentations they have used. So in a batch, so they are mainly taking a n-size batch from an unlabeled dataset. So then for each image in that dataset, they are applying those two augmentations. So each image will give two images, so the n batch will finally give 2n images in a batch. And these two augmentations, they are calling it a positive pair. And the other ones are all, they are taking all the other ones as negative pairs. So in a batch, there are two positive. So if you take one image, there are two positive images and 2n minus 2 negative images. Here in this base encoder layer, they have used a ResNet layer for that. In this MLB layer, it's a projection layer. So they have used a fully connected layer. The hidden layer uses a value activation, and this one is just a linear activation. So the output corresponds to this. So in the loss function, what they are doing is they are maximizing the similarity between these embeddings in Z space. So for similarity, they are using cosine similarity of those Z embeddings. They have also used this tau parameter. It's a adjustable temperature parameter. So they are using it to scale the inputs and widen the range. So the basic intuition is, so if two of those images are similar, they should be close in the similarity would be much higher, and the cosine similarity is higher. And in the loss function, it's a softmax loss. So we are getting the similarity of positive examples divided by the positive similarity of negative examples. So for example, if we take a batch of 2, so if we get one positive example, we can find the softmax similarity like similarity of these two examples divided by the other negative examples. Then again, so they find the loss function for these images and also interchange these images and find the loss function again, and then take the average of those for every positive example in the dataset. So they are calling it NTXent, the normalized temperature scale cost entropy loss here. So yeah. This one is like 1 2 2 1 3 4 4 3.
There is a loss between dissimilar examples.
So there's no. So they are finding this cosine similarity. So there are no explicitly loss function between dissimilar.
So no mining also for?
No. So they haven't used any mining and memory bank for this one. So they just get the bed size of n. Yeah. So this is the algorithm. So we get a one image at a time xk. So we apply the augmentations in one side, augmentations the other side, and we are finding the loss between these two images and the other negative examples in the wedge, and find the average of those in a whole wedge. So important implementation details. So they train the model with a large batch size. So as they aren't using any memory bank or any mining for negative examples, they have used a large batch size like 8,000, so that they can have a large amount of negative examples per positive pair. And to stabilize the noise given by large batch sizes, they have used last optimizer. So it's like it stabilizes the noise given by large batch size. So one key takeaway from this paper is the data augmentation is very crucial for contrastive representation learning. So earlier approaches define contrastive predictions by changing the architecture of the model. But here, in authors only simply use a data augmentation method to define the predictive contrastive prediction task. So for an example, this random crop. So this is the image and these are two crops. So the contrastive prediction task becomes the global to local view predictions here. And this one, the adjacent view predictions. So it's mainly the contrastive prediction tasks done through the augmentation. And this one also decouples the predictive task from other components such as neural network. Although they have used only 3 augmentations in the paper, they have studied some set of transformations like addition studies. And as ImageNet images are of different resolutions, so random crops are any random crops are typically applied. So they cannot study the other augmentation in the absence of cropping. So cropping is always there. So what they have done is they have always cropped and resized to this image size. Then to one path they have taken the same image. To the other part they have done any single or pair of augmentation for the ablation studies. So here you can see that we have the first transformation, second transformation. So this transformation is done only to this path, and this one is just the cropping and resizing. The diagonals here, diagonals represents only one transformation is added to that path. The other non-diagonal elements have those two transformations or augmentations done sequentially. So we have these high values on these two ones, like the color and crop, and also mainly for the color and crop they have taken some higher values of accuracy. So the reason for that is without color distortions. So if we take an image and get random crops from that one, if you get an image and take random crops from that one, the color histograms, the histograms of pixel intensities are the same. So if we get one image and apply random crops, the histograms of pixel intensities are similar. So this is for one image and this is for another image. So if we don't do any color distortions, the neural network model will try to differentiate the images just using these color histograms. So that's why doing color distortions here gives a high score for accuracy. So if we do any color distortions, the histograms becomes different. So to further demonstrate the importance of color augmentations in contrastive learning, so they have increased the color distortion strength and measure the score. So compared to supervised learning, the contrastive learning task benefits much more from these color distortions. So in supervised learning, the accuracy is almost similar, but in the contrastive learning task, the accuracy increases by a great deal. Then for the encode and projection head, the main key finding is that contrastive learning benefits like more from bigger models. So if we go from this, the blue dots are our trained examples for 1000 epochs. So this one for 1000 epochs. The red ones are for blue ones for 100 epochs. Red ones for 1000 epochs. And in the blue ones, by increasing the width of the model, the accuracy increases by a good margin. Here also. And also increasing the training time, it also increases the accuracy of the model. So what they are basically saying is the effect of the model size is much larger than in effect of model size in contrastive learning is much larger than in supervised learning. Then for this projection head, they have tried using three different linear projection head, non-linear, and without using any of these projection head, and just getting the HI to minimize the loss, maximize the similarity. So here also they have found that using a non-linear projection head results in much better top-one accuracy in ImageNet datasets. The other thing is, for any downstream task, they are basically removing this part and only taking this one. So the reason for that is in this layer there's a great deal of loss of information because the Z equals GH, that layer is trained to be invariant to data transformation. So there's some loss of information there. So this layer is only taken for some downstream tasks. And it is represented here using this TNC map, using this H and also GH. So by using H, the clusters are much more visible and separated than using Z.
That's for downstream tasks.
Yeah, for downstream tasks. Then if you look at loss function and the batch size, so using so they have to properly use the normalization and proper temperature scaling. So if they don't use this normalization and proper temperature scaling, the performance is significantly worse. So they have the best results are the best results are under L2 norm and the tau being set to 0.1. And also contrastive learning, it benefits from larger batch sizes also and training for long epochs. So the intuition here is by increasing the batch size, we are getting more negative examples per positive image. And also by training for a longer period, we are also getting much larger size of negative examples. Yeah, so if you compare with state of the art, there's around 7% really important over previous self-supervised algorithms. And also, if we increase the width of the model, it also reaches the supervised learning models as well. Then they have used it for a semi-supervised learning task. So they have got this data set and sample 1% of the data in those classes and also 10%. So using only those 1% and 10% data, so they have got much higher accuracy than previous self-supervised algorithms. For transfer learning also, they have used 12 different natural image data sets and also they evaluated in both linear evaluation, like they fixed the feature extractor and only trained the final layer, and also fine tuning the whole layer. So in both of those two as well, the accuracy scores are much higher than the previous implementation, and also here it's better than supervised learning as well in some of the data sets. So the main conclusion from this paper is SimCLR is a simple architecture but yet effective self-supervised framework. And also the superior performance is not due to any single design choice but a combination of design choices, like the combination of data augmentation and the batch sizes. And so this paper basically revealed some important factors that enable effective representation learning. For implementation, so I implemented this SimCLR on STL10 dataset. So these are some of the images and the augmentations done. And let's go to results. So this STL dataset has 10 classes, and each class has 500 labeled images. So by getting only 10 of those images, we are reaching about 62.5 test accuracy. And if we get all those 500 images, we can reach around more than 80% of the accuracy using contrastive learning. So to contrast between this and a simple classifier using supervised learning, so a supervised learning classifier got around 73.31% of accuracy on this dataset using the 500 labeled images. So in these using 500 images, so accuracy is much better than a supervised learning.
So that is actually training in SimCLR and then fine-tuning
on
using
the
grounded
images.
What's that STL dataset?
there are 10 classes and 500 labeled images for each class, and there are non-labeled datasets images as well.
Here the SimCLR is trained on ImageNet or something and then find into...
No, it's trained on this one, this here.
Why is that projection head so important? They have proven that using results, right?
Yeah, so they have done some ablation studies. Yeah, so it's mainly they have done some studies and found out that using an unlinear one is the accuracy is much better.
Program.
Although you show two branches, they are one single shared network, right?
What was the argument to increase the results like that?
There was no argument actually. So we are just shown the results and saying like it's much better using that.
It's a single linear layer, right?
Yeah, it's one only layer.
Did you study about the SimCLR version 2?
Yeah, so there are, I think the SNet architecture is changed to use some attention layers as well. But I didn't go through the table.
Not from the same one.
Not sure.
So the alternative for contrastive learning is masking.
Yeah.
Treshan, in the loss function, the positive pair we interested, the other all pairs than what we interest are in the denominator, or
Yeah. So,
including there are two positive pairs. So the other positive pair is also in the denominator.
no, so this IG is this is calculated for just one positive pair.
One pair, yeah.
One pair. So you take one pair and find the similarity, and this denominator has all the other pairs.
Other than
Other
the
pairs means like this one.
flipped one.
Yeah.
Flip pair and all the other negative pairs.
Yeah.
Actually, it's for one. There are images for one. There are different
No,
images.
it's actually, let's say it's for one image actually. Let's take an image and we get the augmented image as well. So the numerator is for that pair, and with that single image we are taking the augmentations of other images and get that the negative pair.
Shouldn't that right.
So both ZI and ZI is here. and that is calculated to all the images in the batch. I'm getting an average.
The rippling thing actually happens in the denominator, so there's no.
Yeah. So to maximize the similarity, I think we can maximize this one or reduce this one. So the denominator rebels and the other one attracts.
My issue was the same thing we need to make close is also in the denominator.
Yeah, so
that makes the expansion like inside between 0 and 100. So if we increase the similarity, then the loss becomes more close to 1, therefore reducing the loss. So even if the similarity of other images the scores are somewhat high, if we can produce a very high similarity score for the same images, like single set of images, then still we get the small loss function. So it's kind of balancing on the proportions as well.
Yeah, so previous studies have used they have kept a separate negative examples memory bank. So and then compared positive one with the negative one. So the difference here is they are using actually some of the positive examples as negative as well. So if this dataset contains another image of the cat, so that would also come to the denominators. Yeah, denominators.
Shall we go? Any other questions? So it's time for Treshan to